In a previous video, we talked about valence bond theory and how we used it to understand molecular bonding overall. Specifically, in that section, we were talking about diatomics, but we also recognized there were some problems with it. So we're going to start moving towards another theory that does do a better job in some regards at explaining how bonding actually works in molecules, and that's molecular orbital theory. So let's first identify why we need to go past valence bond theory. And in that previous video on valence bond theory, we noted that it doesn't predict the properties well. Specifically, we're thinking about magnetic properties. I think the example there was O2, and it didn't correctly predict that O2 would be paramagnetic. Another thing that valence bond theory has a problem with is actually carbon. It doesn't really adequately explain how carbon binds with tetravalence. And the way we've gotten around this in the past was using hybridization. So thinking about the sp3, the sp2, and the sp carbons, that's actually pushing away from valence bond theory. Valence bond theory does not naturally do that. It says, oh, it doesn't work right with valence bond theory, so we'll use these hybridization models instead. We've also talked a lot about energetics for this course, and when we were talking about valence bond theory, I didn't really talk too much about energy. It was just an ancillary component there. You could really push it in, but it really does a bad job thinking about the electron's energies overall. Another big problem is how it actually works, because remember, when we form a bond in valence bond theory, we said, all right, we're going to form a bond between the two hydrogen atoms. We're saying specifically in this nomenclature that, hey, we've got two electrons in that specific location. And we remember with quantum mechanics, that's not a good thing. So Heisenberg uncertainty principle said that this was not something that quantum mechanics really allows for. We need to have a lot more flexibility. So again, valence bond theory doesn't do what quantum mechanics says is actually the case. Valence bond theory also doesn't really work for ions. We kind of left that out when we were talking about this entirely, where we said, okay, yeah, you can bring in ionics, but it doesn't even seem to make sense. So when we try to bring it in, it's not easy, and it really looks really ugly when we deal with any type of ion. So really, we're seeing just a collection of issues here that say, hey, maybe valence bond theory isn't the best way to do this. Maybe there's a better way that we can understand molecular bonding. And the way we're going to do that is through what we call molecular orbital theory, which has a few key tenets to it. Specifically, we're going to say that in a molecule, the electrons are in what we call molecular orbitals. And a molecular orbital is kind of what it sounds like. It's an orbital over the entire molecule. So for example, over here on the right-hand side, we're showing the molecular orbital diagrams of benzene. So here's one where we see an orbital that shows electron density all over the ring. And then other different variants on it that show different ways that we can parse out those electrons across the ring. But notice, in basically every case here, these orbitals are all around. They're not just in a specific location, not localized on a specific atom. They're over everything. This is good because it delocalizes across the entire molecule. That's an important part, because we've never talked about localizing molecules in quantum mechanics, because they could really be anywhere on our molecule. We need to allow for that. Another piece of this that we're going to bring in here is we're going to base molecular orbital theory on wave functions. So again, just like we did with the atomic orbitals, we're going to do the same thing here, where we're going to say these pictures that we have here tell us about the three-dimensional properties of the electrons. And we'll make use of those atomic orbitals by doing some math to do combinations of them. So we kind of saw this a little bit in valence bond theory as the start, but it was really ugly and didn't make a whole lot of sense, and we had to do some weird things there. But in molecular orbital theory, it's a much more simplistic integration of atomic orbitals that we can actually put together. So to make molecular orbitals, what we're going to start with is we're going to combine atomic orbitals with atomic orbitals of similar energy. Eventually, we'll have to talk about the symmetry of those orbitals as well, but don't worry about that now. All we need to care about is the energetics. And again, we're going to pull in this linear combination of atomic orbitals, the LCAO, but now we're going to do it in a much nicer fashion here, where we're going to say, hey, for an entire molecule, we'll just start and say, hey, what is the overall molecular orbital? Well, it's the contribution from the 1s orbital on atom A, the 1s orbital on atom B, the 2s orbital on atom A, and so on and so forth, until we can add up all of those combinations of all of those orbitals on all of our atoms. And again, like we showed before, we're going to have these little coefficients here to tell us how important is that orbital to the overall molecular orbital. Another key aspect here is, hey, we're going to start with a certain number of atomic orbitals. We've got a certain number of atomic orbitals for carbon, a certain number of atomic orbitals for hydrogen. So when we start putting them together to form molecular orbitals, we should start with a certain amount, and we should end with that same number. So if I start with 8 atomic orbitals, I should form a total of 8 molecular orbitals. So nothing gained, nothing lost in our orbital picture. Another kind of corollary to that is, if we add up the energy of all of our atomic orbitals, it should be the same as our molecular orbital energy. So by putting our orbitals together in this new way, we're not creating energy. We're not destroying energy. It's still the same amount of energy. So we're nothing gained, nothing lost again. When we do this, it does make a slightly different picture, because now we're going to actually see that there are 3 different types of orbitals in the molecular orbital frame. There is the standard bonding orbital that we've seen a million times in the valence system, but now we've got 2 new ones that we're going to have to understand: the non-bonding and the anti-bonding. So we'll have to describe what those are and what they mean when they are populated and they are filled in a molecule. And finally, when we're constructing our molecular orbitals, we're going to use the same electron filling rules as we did with atomic orbitals. So in other words, we are going to start and occupy the lowest molecular orbital energy first. So the lowest energy molecular orbital gets 2 electrons. Then we go to the next higher energy, which gets 2 more electrons, and so on and so forth. So we're using a lot of the principles that we talked with atomic orbitals, but now we're just applying that to a molecular system. So this is just outlining what they are and how we're going to build them. We're going to see some examples of these here in an upcoming video, so hang tight for that. But again, this is just the introductory level. So as you're paying attention to this, please make sure, note your questions, your curiosities about this, and we can take care of those in class. Make sure to ask those questions then. So until we get there, be excellent to each other.